Thank you. Well, as a geologist, I can tell you that although Chuck may think rocks rule, that only applies in the inner part of the solar system. What we're going to look at is the outer part of the solar system. We're all familiar with the classical impact structures on the moon and the rocky planets. Through our telescopes, we can observe the geometries of impact structures or the giant impact basins on the moon. And through books and through the internet, we've got a pretty good idea of what these features look like on Mercury and on Mars. Next one, please, Chris. But what happens when a comet, an asteroid, or a large meteor impacts the surface of an icy moon, such as those in the orbits of the outer planets? What do those impact structures look like, and how do they compare with those preserved on the rocky planets? So let's start with a look at the old battered surface of Callisto, one of Jupiter's ice moons. Now, because Callisto is essentially cold and dead, or at least it's supposed to be, the impact features that have accumulated since the beginning of the solar system are still beautifully preserved. Next one, please, Chris. Now, Valhalla, the palace of the Norse gods. This is a thousands of kilometer wide multi-ring impact basin. Let's see if I can actually make this work. Yes, there we go. So all these rings here, these are the multiple rings of the Valhalla impact basin. And superficially, it's very much like the Orientali basin on Earth's moon. It's difficult for us to see from Earth, but with the wobble of the moon, the libration, we can sometimes see parts of it. It's also rather similar to the flooded equivalent of these impact basins, which we call the Imbrium basin on the moon, and that we can see. However, Callisto is made of ice, and ice does not have the same strength characteristics as rock. So it's not surprising to see significant differences. Next one, please, Chris. Now, look at how shallow this central depression is at Valhalla. This is certainly not one of Chuck O'Dale's big holes in the ground. Press forward twice, Chris. That way we get rid of that circle, and we'll see what we get next. There we go. All right, so now let's look at the number of concentric ridges that surround the impact site. It's at least double, if not more, the number for the best lunar examples. In addition, there are no rays of ejecta. There are no radial rays of ejecta coming out from the impact site. So everything points to something relatively soft. In other words, this impact was more of a splat than an explosive impact. And that would also explain the low relief of these concentric ridges and the shallow central cavity. In other words, the initial impact structure, the hole, if you will, would have collapsed rather like melting ice cream. Now, bear that analogy in mind, because I'll come back to that one a number of times. So the next one, please, Chris. Okay, so here we've got a detail of the previous image. These concentric ridges, although they're low, they do have some topographic relief, though as you can see here, enough relief to cast a good shadow when the sun's low on the horizon. Next one, please. But here's the surprise. In addition to these 10 or so principal concentric ridges or scarps that we could see in the previous photograph, there are many minor low-relief scarps in between them, as indicated by the red box. And this is another feature that we just don't see on the moon or on Mercury. Next one, please, Chris. So here's another close-up on Valhalla. Valhalla is an old impact basin. Next one, please. Next one, please, Chris. Thank you. And as you can see, as the box illustrates here, we can tell that it's old because of the density of small impact craters that have scarred the concentric ridges of the basin itself. You can see these small impact features there everywhere. But this is not the oldest part of Callisto's icy surface. Other parts of the moon have even higher impact crater densities, and that means that they're even older. Next one, please. Now, I've shown you this image of impact craters on Callisto in a previous talk. The impact craters are pretty obvious, and they show some similar features to those of the rocky planets. For example, the larger craters have central peaks, like this one here. There's a central peak, just like you'd expect to see on Earth's moon. But there's something a bit odd about this battered, icy surface. You notice how the walls of this crater here, they seem to be eaten away, and so do these over here, and even these ones over here. Next one, please, Chris. And if we focus on that large crater in the red box, you can see that the walls even seem to have moved around. In other words, they've actually slid down into the crater pit. Now, for physical reasons that I don't yet understand, I've looked on the internet, but I don't see anybody directly explaining this to me. The ice of Callisto's surface is capable of crumbling and moving around like sand, which is kind of strange behavior for ice. So the next one, please, Chris. Now, Europa is another one of Jupiter's ice moons, but this is one with a very young and very active surface, as we can tell from the very low number of preserved impact craters. Europa is so active that it's constantly resurfacing itself, and therefore it eliminates the older impact structures. Now, even from space, it looks as smooth as a billiard ball, which is a reflection of the fact that Europa's ice is too weak to support the weight of a significant mountain chain like the Himalayas on Earth, or the ring of mountains around the Mare Imbrium on Earth's moon. Next one, please, Chris. However, comets, asteroids, and meteors do strike the surface of Europa. So what do the impact features look like in this relatively weak ice? Well, here are four classics. There's the unpronounceable Pwyll crater. That's Welsh, by the way, and you might tickle your tonsils trying to pronounce that one. The Cilix crater, that is number 2 there, which is much younger than a complex array of ridges in the icy surface of the moon. Here you can clearly see that this crater here is cutting right across these ridges. We talked about ridges in previous talks, ridges in these icy moons. That clearly is a young feature. That's Cilix here, and this is Pwyll. Actually, there'll be a test afterwards. You all have to learn to pronounce Pwyll. The impact ring structure, Tyre, here. You notice the 20-kilometer scale bar down here? Well, it applies to all of these images. So that actually, although it's a multi-ring crater, it's not a multi-ring basin. It's a pretty small feature. It's way too small to be considered to be an impact basin. And then there's this one here, Manannan, another one that's a beautiful one to pronounce, but it's as difficult to pronounce as it is to see. Frankly, if I weren't pointing it out to you, you might not even be able to see it in that image. What all of these impact structures share in common is, again, very low topographic relief, very shallow crater floors, and very low crater walls. So again, this is a function of the inability of the relatively weak ice of the moon's surface to resist the pressures that would be generated by major differences in topography. If you have a hole, a deep hole, kilometers deep, with walls which themselves may actually be kilometers higher than the average surface of the moon's surface, you generate a pressure gradient. You've got more pressure under the high walls than you have actually in the hollow, which forms the floor, if you will, of the crater. And so therefore, you need a strong material to resist the tendency to flow. And because this is weak material, the weak ice cannot actually support the pressures generated by those major differences in topography. Next one, please, Chris. Okay, here's the multi-ring structure Tyre placed in regional context. And there again, there's a 40-kilometer scale bar here, and there is Tyre. Not that big. Only 40 kilometers across, and you can easily see how shallow it is. Technically, this is referred to as a macula. Macula literally means a stain in Latin. And the lack of rays of ejecta is particularly obvious. Now, on Earth's moon, this multi-ring geometry is only found in the giant impact basins. But a structure of this size is clearly just a modest-sized impact crater. Now, this is not the youngest structure in this image. As you can clearly see, it's cut by long ridges of the kind we've already talked about in previous talks. There's a long ridge cutting right across that structure there, and there's another long ridge cutting across the multiple ridges. Now, next one, please, Chris. Now, this is a false color version of the same structure. In other words, NASA has basically put this one through Photoshop and added some colors to it. It looks like a watermark in Europa's surface ice, which is technically referred to as a palimpsest. I spelled it out for you there. The only reason I'm giving you these names here is in case you sort of read this stuff yourself and wonder, what the hell's a palimpsest? That's what this means. It basically refers to it looking like a watermark. Now, the accepted interpretation of these low relief impact features is that they formed in soft, perhaps relatively warm, and perhaps relatively thin ice. Now hold that thought, relatively warm and relatively thin ice, because we're going to come back to that in just a minute. Next one, please, Chris. Now, Tyre is not unique. Next one, please, Chris. This is another macula on Europa, and here the box here actually gets you into the core of it. You can see the concentric features here, the concentric ridges. There are multiple ones here, 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 here. And this time, this is the youngest feature in the image, since it actually cuts all these triple band structures. You see this triple band here made of two high ridges separated by a central valley. There's another ridge, exactly the same kind of structure. They're called triple bands. And this triple band down here is clearly cut and truncated by one of these concentric ridges related to this macula. Next one, please, Chris. Here's the unpronounceable quilt. I do mean it. There will actually be a test at the end. The impact structure, the impact crater itself, is actually this. That little black dot there is a 25-kilometer wide dot in the middle of this white splash zone. Now, in contrast to the previous structures, this one has an enormous set of ejector rays, which are thousands of kilometers in length. Now, look at the scale bar here. That's 1,250 kilometers. And look at these ejector rays coming out from this crater, which had absolutely zero relief on it. Now, because these rays cut across all the cracks in the ice ridges, then this quilt itself must have been a very young feature. Next one, please, Chris. Now, the question is, actually, no, can you back up one for me? There, we're back to a quilt. Now, the question is, why? Why does this impact crater look like a classical lunar feature such as Tycho on Earth's moon? That's the attachment point of the orange, if you like, when you're looking at the full moon down in the southern part of the moon. You can see a crater there with rays which radiate out from it. That's the crater Tycho. Why does it look like a classical lunar feature here when we've just seen that other impact features on Europa are so different? One possible answer is that this impact crater formed in relatively cold and relatively thick, and therefore relatively stronger ice than the Tyre multi-ring structure. This sounds like a pretty good explanation until you go in a bit closer. Next one, please, Chris. And here's a close-up of the quilt crater itself, and you can clearly see this time around there's no topographic relief whatsoever, just like Tyre. So this suggests here that the ice was too soft to support a deep hole with crater walls, all of which puts us back to square one when trying to explain the ejector rays that we just saw in the last image. So the take-home message from the surface of Europa is that impact structures in ice on that moon still remain a mystery. We still do not understand the mechanics and the behavior of impact features on this moon. Next one, please. Next one, please, Chris. Thanks. Okay. Impact structures on the surface of Jupiter's ice moon Ganymede come in two flavors, depending on whether they occur in the older, dark terrain, that's this stuff here, for example, or this stuff over here, or whether they occur in the younger, lighter colored terrain which occurs between. So you can see the lighter colored terrain in through here and around here. Now, in the older, dark terrain, the impact structures look just like those of Europa. You can see them here, here, here. There's some nice large ones. I think you can see those even from the back of the room. They look like the ones on Europa, except that they're more numerous. In other words, the larger ones are generally shallow, with very little relief, and show no ejector rays at all. But in the younger, light terrain, all the impact structures are well formed. They have deep floors, they have high walls, and they're surrounded by very obvious splashy white rays. Look at them down there. You even get them in these smaller ones here and over here. Now, you can see those white rays even from a distance, even as in this image here. So let's go to the next one, Chris. Let's zero in on this red frame. Next one, please. So here's a detailed image of the older dark terrain with three kinds of impact features. First, there are these closely spaced, gently curved ridges that you can see through here, ridges and grooves, and they run northwest, southeast across the photograph. And they're the remnants of a giant multi-ring impact basin similar to Callisto's Valhalla. Next, please. And the grooves have been overprinted by large impact craters, which are therefore younger than the impact basin itself. And notice how both the grooves and the larger impact craters have very subdued topographic relief. So again, we ask the question, does this indicate that the impacts occurred in relatively soft ice? Hit forward again, Chris. And again. Now, the third kind of feature are relatively large impact craters and grooves. The relatively large impact craters and the grooves are themselves battered by smaller, younger impact craters. And these are pretty well formed. They have deep floors. There's a really nice example there and a nice example down there. They have deep floors. They have high crater walls. They even have central peaks. In other words, these are classic impact craters. And these small impact craters look like they formed in relatively hard ice, but it's the same ice that these things formed in, and it looks like soft ice. So what's going on here? As you all know from shoveling your driveways, relatively warm ice is relatively soft. And if that ice gets to cool, if it gets to really freeze, then it's a lot harder to shovel. So is it possible that in this image, what we're actually observing is direct evidence for the progressive cooling and stiffening and strengthening of the surface of Ganymede with time? In other words, there's the initial impact by the multi-ring basin with low relief ridges, which then itself is impacted by, is peppered with impact craters into still soft ice, and they therefore have a low relief. Through time, the ice cools and gets even harder still, and so now the youngest impact craters have that classic crater morphology to them. Next one, please, Chris. Now let's take a close-up at one of Ganymede's impact craters in soft ice, and this is one called Neith, which is spelt down here, Neith. This one here is the one we're looking at. You see the size of it, 150 kilometers. Not only is Neith's topographic relief very subdued, it's inverted. It's not a hole, it's a hill. Here's the outer limit. Next one, please, Chris. There's the outer limit of the crater. And that outer limit is about 160 kilometers across in this very shallow crater. Press forward twice again, please, Chris. There we go. Closer to the center of the crater is a ring of what looks like chaotic rubble. And we know that central rings, instead of central peaks, are well developed in large lunar craters. Press forward twice again, please. And here, right in the center, as I said, instead of a hole, what we've got is a hill. So what's happened here is that the walls of the initial hole that formed in this soft ice collapsed to fill in the hole. And by flowing in from all sides to the middle, the ice produced a dome at the impact site, which is therefore a positive topographic relief. Now, this process of flow in soft material to fill a hole like this is known as viscous relaxation, because the pressures in the ice around the hole that I mentioned earlier are relaxed by the viscous flow of the ice back into the hole formed by the impact. And just so that you don't get the idea that this is something weird and unique to Ganymede, next one, please, Chris. Here we are on Callisto. This crater is called Doe. You can think of this as Bart's crater, if you like. There's the outer limits of it, and here's the scale bar of 25 kilometers, so that's a good 50, 60 kilometers across there. Go forward twice, please, Chris. And here's the outer limit of the shallow crater, and there we have, there's the shallow crater, and there's the dome in the center here. So this is a relatively common phenomenon on these icy moons. Next one, please, Chris. And again. There we go. Okay. In another part of Ganymede's surface, we see a wide expanse of light, young ice with large blocks of older ice floating in it. So here are the large blocks of dark, older ice, and they're floating in this light-colored, younger ice. Notice how the impacts in the younger ice are very different from those in the dark terrain. Just like Twilth on Europa, they're very splashy and they have extensive white ejector rays. You can see them here beautifully. Lovely classical craters, lovely white ejector rays. Next one, please, Chris. The one exception to this is circled right here, where a splashy crater has formed in the dark ice. That was the ice that had the very shallow, low topographic relief impacts. But that simply tells me that this particular patch of dark ice is actually very thin. And what's happened is that the impact has gone right through it and has actually managed to dig into the underlying light-colored ice, which I'd suggest is perhaps stronger. This is what, next one please, Chris. This is what the craters in the light young ice on Ganymede look like when you're in close up. They're well formed with deep floors, high crater walls, central peaks, especially in the northern one right here, and well-defined collapse structures preserved against the crater wall in the southern one. You can see them right there. This looks exactly like the kind of thing you can observe on the moon when you look through your own telescopes from your own backyards. The beautiful preservation of these classical impact crater features tells us that this young ice must have been strong like rock, and presumably that's because it was relatively cold. Next one, please, Chris. So, can we explain all the differences between the subdued, older, and the splashy, younger impact craters on Ganymede in terms of hardening of the moon's surface ice as the temperature decreased with geological time? Well, I'm afraid we can't. And this picture here shows why. This is an impact crater chain that crosses the boundary right here between old impacted ice and less battered younger ice up here to the northwest. The crater chain was formed by an impactor that broke up into separate bodies just prior to impact. So it's one event. It's one instant in time. And notice the lack of ejector material associated with the crater chain component here in the older ice. And next one, please, Chris. But notice the splashy light-colored ejector associated with exactly the same crater chain in the younger ice right here. This is all the splashy ejector material. The craters look similar in both parts of the chain, so it's reasonable to assume that the ice was equally strong in both older and younger terrains at the instant of impact. But I have no idea how to explain the distribution of impact ejector in this image. I've thought about it, and I'm completely stumped. I cannot tell you why there's no ejector here and there's ejector there. So again, I guess the take-home message is that impact features in even this icy moon still require a lot more explanation. Next one, please, Chris. Okay, I want to end this talk with a brief look at what happens when a relatively large impactor hits a relatively small icy moon. There are, in this image here, you've got three views of the crater Odysseus. That's this whacking great thing here. This is all the same picture of it. These are three views of Odysseus in Saturn's relatively small ice moon Tethys. And there's a scale bar down here, about 500 kilometers, giving you an idea of just how small Tethys is and just how big Odysseus is in comparison. Now, compared with the size of the moon Tethys, Odysseus is so large that its floor actually curves with the moon's surface. So if you were standing at the foot of the crater wall, the other side of the crater would be out of sight beyond your immediate horizon. Now, the relative sizes of the moon and the impactor were such that the moon only just held together when it got hit. It's probable that icy Tethys was soft enough, as being ice, to absorb the impact rather than shattering under it. Next one, please, Chris. And finally, here's Miranda. This is the strangest moon in the entire outer solar system, and it orbits around Uranus. Again, it's a relatively small moon. You can see the scale bar here, about 500 kilometers across. Its surface comprises huge angular blocks with a strange banded terrain with very few impact craters. These are the blocks I mean. There's another big one down here there. This is the clearest one. This is the best focused. And you can see this banding in here. And there's not that much in the way of visible impact cratering there. But those blocks are surrounded by densely impacted terrain here. See the dense impacting here. And here's a close-up of the same thing. That's, in fact, this corner right here. There's the banding, and that's about, I guess that's about the edge of the block there. Am I right? No, actually, that's that white band there. So we're entirely within this block here. The impact crater distribution suggests that the banded terrain is younger because there are less impacts. But, next one, please, Chris. That's now showing you where that detail there is that box there. The internal structure of the banded terrain appears to be folded, rather like a chevron. That's the same thing as sergeant stripes. And the fold appears to be truncated at the terrain boundary. There's the fold there. And the banding seems to be cut right off right there. Geologically, that suggests that the banded terrain was folded first and then included in the surrounding terrain. And that's in apparent contradiction to the sequence deduced from the impact cratering. Now, the initial explanation when this was first observed was that, unlike Tethys, Miranda did indeed explode and shatter when it was struck by a massive object, but that its exploded components didn't separate by much. And they were able to accrete back together again to form this Frankenstein moon by gravitational attraction. Now, planetary scientists have since realized that this simply won't work, and are now suggesting that the bands in the banded terrain actually represent fractures at various angles that guided the eruption of ice volcanism, which we've talked about in previous talks, that replaced the older ice, and that the larger blocks of banded terrains are bounded by large geological faults that explain the abrupt boundaries. So these would have been fractures within these blocks here, and ice would have come up from within the moon along these cracks, multiple cracks to form the banding, and that then later geological faults through here would have actually chopped off the banding in this image. Now, I've got to tell you, this is a pretty sketchy theory, but this is the most modern thinking. But it's better than a model of an exploded and reassembled moon to explain Miranda. So I end this talk on impacts in icy moons with the case of the impact that never actually happened after all. Thanks for listening. Yeah.
Would that not be spelled N-Y-L-L?
N-Y-L-L. No,
or
that.
you had the other one which was flip?
Oh, no. You have to listen very carefully. Hang on, let me go close to the microphone. The P-W-Y-L-L is Pwils.
Okay.
You actually have to sort of do something funny with your tongue between your teeth at the back. The only reason I know this is I did my undergraduate degree at the University of Wales. There are many other places that I went to with even more difficult pronunciations.
Any other questions? Yes, Pat?
Do we know what causes the dark terrain on Callisto?
No, but yes. Do we know what causes the difference in color, essentially, between the dark terrains and the light terrains on various of these moons? We don't know, but we do know that ice will change its color according to a number of simple parameters. For example, grain size. You can actually see this if any of you actually go north or if you do any ice fishing. If you do ice fishing, you'll know that as you go through really good solid ice, when it's in the depths of winter, that ice is blue. And as the season begins to progress, the ice will eventually, what's called candle. In other words, it'll then turn a white color and it gets dangerous to walk on, even though it's still thick. So if you have pure ice with large, clear, unaltered crystals, then it'll have a one color. If you then come along and damage it, either because you change the grain size or you fracture it with many fractures, it'll then change from a darker color, the darker blue, the clear blue, to a light color. That may well be what's actually happened. And frankly, the only way they're going to find out is to land. Pat?
There are similar analogies when we were doing ice reconnaissance up north. They had all kinds of classifications for ice, Bergy bits, Gromlins, and they did have different colors. So
Yeah.
it might be the same.
Yeah, Pat's pointing out that those who actually work in the north, and she was referring to Attila specifically, that there is a classification of various ice types and those different ices, and it's usually their structure that's the difference. They do have different colors. What's really happening is that the light is being refracted within the ice differently, or refracted off the ice differently according to the structure.
Are there grains in the ice?
Oh, yes.
Material? And how would the solar radiation affect that?
Oh, well, let's put it this way. It's not very warm on those planets. When I was mentioning warmer ice becoming colder, I'm talking about going from, well, something in the order of, say, minus 150 down to a couple of degrees above absolute zero. I don't think solar radiation would actually affect the crystal structure. I think it's more likely to be either some form of ongoing bombardment and a response to that, or a recrystallization.
You mean physical bomb?
Oh, yeah. That could be bombardment by dust, for example. would be enough to actually damage the ice enough so that it then recrystallizes with a much finer grain size, for example.
Oh,
Simon, this is a little off. Isn't Ganymede planetary size really? Isn't it about as big as Mercury, I believe? Ganymede, the moon Ganymede. Yeah, is it not of a planetary size?
It's of planetary size. It is indeed. Yeah, it's about the size of Mercury. They are large moons. Chuck, you had a question?
Yes, regarding the different crater types in the same area, suggesting the ice was melted and hardened. Could that large impact have caused that ice to sort of be in a melted state with all the energy of the impact for a long period of time, causing the different stages of cratering? Or was that?
No, I doubt it, because the large impact to form the Valhalla Basin, it's quite clear that the ice nevertheless responded as a solid. If it had transformed into a liquid, then what we would have seen would probably be a large circular structure representing the initial impact, and then filled by something looking rather like the lavas which fill impact basins on the moon. In other words, there wouldn't be that internal structure, because the concentric ridges are part of the impact basin itself. They would not be there.
Brian, I think Brian was next.
Simon, can tidal forces change the crystalline structure of the ice?
If you could repeat that.
That's a good question. Can tidal forces change the crystalline structure of the ice? Yes, they could. But I'd be hard-pressed then to explain as to why is it that some of the ice is changing and some of it's not. What is clear, Chris, can we go back to the image of the first image of Ganymede?
Further back?
No, we want to go further back to the first picture of Ganymede itself as a moon. There, one more, I think it is. There we go. Here's the light-colored ice, and if you look, remember when I gave my talk on fracturing, on linears, I pointed this out. The light-colored ice has actually penetrated into the older dark-colored ice, rather like veins. Look at them going in through there. They're actually gigantic. They're tens of kilometers across and hundreds of kilometers long. That means that this light-colored ice was mobile, and it probably came up from within the moon, and as it's flowing, it wouldn't have been flowing as water, or even as water with ammonia, in other words, cleaning fluid. It was probably flowing as relatively warm ice, and as it does that, it actually starts to granulate itself. So even if it had had large crystals, those crystals would have been broken down. Paul's nodding because Paul was a metallurgist, and he knows this is exactly what happens in metals. And that's possibly part and parcel of the explanation on this moon as to why the difference in color and potentially difference in grain size.
And one more.
Yeah, I guess you didn't talk too much about the chemistry. I mean, are these all water ice moons, or and I guess the follow-up question to that would be: has anybody tried to do like the mechanical modeling of that, just in a with small projectiles, in a frozen?
Yeah, the question is, I hadn't said much about chemistry, and is this just water ice? And has anybody done any modeling in the lab to see what would happen if you actually chucked something at equivalent ice? Now, the reason I didn't mention the chemistry is I've done that in a previous talk. If this had been water ice, then this ice would be so hard that none of the structures I'm talking to you about would actually have formed. You had to soften it up to get it to flow at all, and the theoretical chemistry says that there should be ammonia mixed in with this ice. That's why I referred to the ice actually as cleaning fluid, frozen cleaning fluid. I don't know whether people have actually done experiments specifically on this, but I'd be really surprised if they haven't. I know they did experiments to try and determine whether or not the classic craters of the rocky planets and the moon, our moon, were actually the result of volcanism versus impacts. And it was only about 40, 50 years ago that that was resolved. And in part through experiments. Some of those experiments were done in the late 19th century, by the way, and they were pretty strange contraptions. I'm sure somebody has, but I've not come across it.
I have a question. Why is this color photograph black and white, and then the close-up is in color? Why is that? Is the close-up on this one in color?
Yeah, just looking there.
Oh, that's sort of a sepia tint that I think they may have added. But I think it is essential. All the untouched images I've seen are black and white.
Okay, last.
Yeah, okay, on this shot here, Simon, and this, a question to the geologist, I mean, with the large areas of harder ice and softer ice welling up, that's reminiscent of a tectonic system. Does that apply? Does the tectonic model apply?
This is a very interesting question. This, as pointed out, this looks a bit like continents on a planet that's got a tectonic system. You remember I talked to you about plate tectonics and the idea of plates moving around and interacting with each other. If this were the case, we know from the way that plate tectonics works on the Earth, I talked to you about this, the idea that the molten material from inside the Earth comes up in the middle of the oceans as the continents are moving away, and that the ocean floor plunges down beneath the edge of the continents as the continents are coming together. Then we should expect to see similar kinds of features to what we see on Earth. Mountains along the edges of the continents where the ocean is going down, or where collisions are occurring between blocks, or we should see volcanoes, even ice volcanoes, and I've talked to you about the existence of ice volcanoes elsewhere. We should see them in the middle, say, for example, if these two blocks were pulling apart. And so we don't see those kinds of features. This is probably, rather than horizontal movement as in plate tectonics, this is probably vertical movement of ice from within the once warmer moon. And again, when I say warmer, I still mean minus 150 degrees centigrade.
Simon, thank you very much.
Thank you.
Thanks so much. And,